Hello, my name is Dwiref.
My name is Sid, and today we're going to be talking about object detection, particularly with the single-shot multi-box detector, or SSD. Our project aims to use TensorFlow and Keras to implement the SSD architecture. Additionally, with our train model, we hope to validate the performance on relevant object detection datasets, such as COCO, which is the Common Objects in Context dataset. Additionally, once our model is trained and ready, we want to convert it into a web-based format, TensorFlow.js, and deploy it on a dynamic web application to allow for real-time object detection. Lastly, we want to discuss the SSD and how its architecture stacks up against other potential object detection systems. Our discussion is going to start with a quick overview of object detection, followed by an understanding of RCNNs as well as their drawbacks. Next, we'll move on to SSD itself and discuss its architecture and why it works so well, followed by a code walkthrough of both our TensorFlow model as well as the web application. And lastly, we'll conclude with a real-time object detection demonstration. Now, object detection requires a few building blocks. First of all, we need identification of the objects in the image, and this is done using traditional image classification. Next, bounding boxes are drawn around the objects that are found in the image, and these boundaries are then fine-tuned using regression. So this means that object detection depends very heavily on traditional computer vision techniques such as image classification, segmentation, and localization. Now, a naive strategy for object detection is to use a sliding crop-based method. So as we can see here in these images, the blue box is drawn around a specific crop, and this crop is then passed to a classifier, and objects within the crop are detected. However, this means that this crop needs to be repeatedly moved around the entire image at varying sizes and varying centers. Now, since an image can appear at different locations, aspect ratios, and sizes, this is very computationally expensive because the crop must be put at numerous different aspect ratios and positions. Next, we could improve this method using RCNNs, which are region proposal-based CNN classifiers. So, as we see in the image, a convolutional layer is applied on top of the image to produce feature maps. These feature maps are then passed to the region proposal network, and regions are proposed. Additionally, the same feature map is pooled using region of interest, and the proposals and this new pool layer are overlaid to perform detection on the potential regions. Now, while this is still a better approach than using a naive crop-based sliding window, there are still a few drawbacks. First of all, this is very computationally expensive and slow for real-time applications. This is because the proposal network often produces on the order of 2,000 different proposals, and each of these proposals needs to be gone through and classified to detect for objects. Additionally, creating the feature vector for each of these proposed regions is very slow and expensive. Additionally, one final drawback is that RCNNs require 3 different models to be trained. We need a base model for traditional image classification, which is then fine-tuned over the regions. Additionally, an SVM classifier is needed. And lastly, we need regression to tighten the fit around the bounding boxes and properly find each of the objects.
Okay, so having looked at the earlier architectures like the RCNN, we're now in a position to take stock of what we've learned and try and see what kind of questions we have to ask to be able to pick a better object detection pipeline. The first question you want to ask is regarding efficiency. Can you derive boundary boxes and their respective classes directly from the feature maps in one single shot? Secondly, you have to wonder why use an SVM when a softmax layer will do. Thirdly, why do you need to resample the pixels from the feature maps for every single object size variance when you can instead learn multiple multi-scale representations from the same image and use that instead? Finally, can you design the approach in anticipation of this kind of multi-scale learning rather than trying to use a standard pre-trained model like a VGG and then knock some classifiers on top of it? Essentially, can you make a multi-scale design for the architecture for object detection? So here are a couple of eurekas which the authors of the SSD paper use to finally formulate and design the architecture that becomes the SSD. The first is, why not treat the initial proposal that you can get as a guesstimate rather than trying to use a sliding window approach or use a dedicated region proposal network. Why not do it in a much more simpler fashion and let the classifier / architecture do all the hard work? Secondly, if we encode the 5 parameters that mark the object detection, which would be the bounding box parameters, the height, width, the spatial coordinates x and y, and the 5th parameter being the object detection confidence score. And why can't we just use a convolutional filter to learn from those representations rather than trying to use something like an SVM, which sounds like a contrived thing to do if you're going to be using deep learning architectures anyway in your object detection pipeline. There is one caveat that has to be kept in mind, which is that convolutional layers reduce spatial dimension and resolution, because successive convolutions will lead to a shrinking of the receptive area for the inputs, and that's kind of a bad thing when you're trying to classify and detect objects that belong to multiple classes and also could be of extremely varying sizes within the scope of the image resolution itself. So it turns out that the SSD solves this third problem by making independent object detections from multiple feature maps that are pulled using skip connections from successive add-on layers on top of the architecture, which we will see represented in a figure in a short minute. So to briefly summarize what the SSD does, well, it first gets a set of default boxes over different scales. Secondly, there are feature maps that are going to be generated and learned corresponding to each of these default boxes. And finally, the predictions from multiple scales of feature maps are going to be combined to get one final presentation of the object detection score and the bounding box. The upshot of this architecture is that there is a speed improvement which comes from not having to use a dedicated region proposal network, which is what primarily slowed down some of the earlier architectures that were used in object detection. So that finally brings us to the architecture diagram. As you can see, there's a standard RGB input image. The first section of the SSD architecture is essentially any dense network that can learn a vast array of features. So in this case, the authors chose to use the VGG16 as the base network, on top of which they've stacked up a couple of extra layers for multiple multi-scale representations, so that you don't lose the receptive field over so many convolutions. Because in a network of this depth, you're bound to lose some finer details and features as you keep on convolving from one depth to the other. So with this kind of approach, where you have a detection being sourced from each convolutional layer, you're making sure that there's no loss of spatial resolution. So with this, we can finally move on to take a look at the code for the SSD in TensorFlow 2. As you can see, there is a base network, which is the VGG16, just like the original paper, on top of which there are some extra layers which are used to sort of increase the span of the multi-scale representations that are being learned. And from these, you're going to have skip connections going out to the detection layer at the end, from which you can basically do a fine-tuning of the predictions from these multiple predictions. So the loss functions involved in the SSD are fairly simple. For the classification, we're using a sparse categorical cross-entropy loss, which is fairly simple and quite popularly used. For the bounding box regression, where we're trying to tune the parameters that govern the position of the bounding box and the height and width of it, we're using a form of smoothed L1 loss, which is called the Huber loss. Fortunately, Keras provides an implementation of that, so we can just call that from the relevant module. On top of that, in the project directory, there are a couple of other files that help with dataset handling, with the training itself, with the testing. There's a file where the network is defined. There's some configuration utilities and a couple of code for the bounding box initial guesstimate, where you have to take into account the intersection over union loss, compute the area of the bounding box that's being taken into account, and so on and so forth. Finally, with that concluded, I think we can look at some of the outputs that this network can provide after 50 epochs of training. So these are images from the VOC dataset, from the 2012 iteration of that dataset, and as you can see, it seems to be performing really well. You have this image here, which has an airplane and a couple of tiny people, relatively speaking, and they are being detected correctly. There's even a airplane in the background, which is not so well resolved as the one in the foreground, and that's being detected correctly as well, which indicates that this is really robust to multiple scales of the same kind of object in an image, which is what the original design goal was. Finally, there's a couple of other images that we can look at. So you have a dog here, it's been correctly found. There's a chair that's also been correctly detected. This seems to be a bit of a strange output where the chair's been detected twice, but those are minor issues. Here you have a sheep that's been detected. Here's another image where a bottle's been detected, a person's been detected, and interestingly, you notice that there's a couple of picture frames in this picture, and it seems that the person in the picture frame has also been correctly identified as a person, which is really good to see. So yeah, that concludes an overview of the SSD in TensorFlow.2.
Here's a quick walkthrough for the code that was used to develop the dynamic web application. So at our root directory, we have a bunch of React.js necessary scaffolding files, but more importantly, if we look inside the components and see the main SSD page component, we can see how this object detection is actually working. So we're using this TensorFlow models Cocoa SSD library, and first we start by enabling the webcam in the user-facing mode. So essentially, the front webcam is being used. Then we use the stream and take each of the images extracted from the stream. Here we're loading the model using our pre-trained model, which we've saved in our assets directory, and whenever the webcam detects an image, it passes it to the model and makes a prediction. Then it moves on to the next frame and makes predictions for those. Now in this render predictions function, we're seeing that each of the predictions gives us the dimensions for a bounding box. Now these bounding boxes are then drawn onto the canvas. At the bottom we see the raw HTML code used to produce the bounding boxes. Here's a quick demonstration of our web application, which does real-time object detection. So as you can see in the center of the screen, we have a web camera which is detecting me and putting a bounding box around my face and calling it a person. Now as an example, I can put a water bottle and it detects that it's a bottle. Now this is using SSD as the object detection architecture. Additionally, it's using the front-facing web camera, and it uses React.js for dynamic page rendering. Now in the next page, we can take a look at YOLO. So as you can see, again, the camera is present. However, it's taking a few seconds for the model to load. One thing we can easily see though is that YOLO is a bit slower in making predictions, at least for this practical web example. This is because it runs at a much slower frame rate. Now as you can see, YOLO again is able to detect my face, and it also successfully detects the water bottle.